So in the previous video, I derived the ideal rocket equation for you, and this is the answer that we got, that the change in velocity is equal to the exhaust velocity of the propellant times the natural log of the initial mass of the rocket divided by the final mass of the rocket. Now, looking at this equation, we kind of run into some problems. Ideally, our change in velocity of our entire rocket needs to be as high as possible. So we need to get our change in velocity as high as possible to be able to get out of the atmosphere of Earth. So the only way to do that is we have two options. Option number one is to change our exhaust velocity, or to increase our exhaust velocity. We can do that, but it's only an incremental improvement. Or we can do option number two, which is to increase our initial mass and decrease our final mass. Once we do this natural logarithmic function over here will greatly increase. It's going to actually exponentially increase because it's a natural log function, and we'll get something very, very different, and our delta V will increase dramatically. Well, how do we do that? Well, rocket scientists have already come up with a way of increasing our mass and decreasing our final mass, and they call it rocket staging. Rocket staging. And when they stage a rocket, I'll show you a picture of a rocket being staged right over here. When you stage a rocket, you have essentially a big rocket carrying a smaller rocket. So let's just annotate this a bit. Let's say that this is the mass. This is the mass of the structure for stage one. This is the mass of the propellant. This is the mass of the propellant for stage one. And this is the mass of the structure for stage two. And this is the mass of our propellant for stage two. And finally, this is obviously the mass of our payload that we're trying to carry to space. Now we can rewrite our mass equations to take into account this multi-staging, and we can rewrite them as follows. We can say that the initial mass of stage one, in this case, is equal to the mass of the payload plus the mass of our second stage structure plus the mass of our propellant that's needed for our second stage plus the structure for our stage one plus the mass of our propellant used in the stage one burn. Now, after our stage one has fully burned, and we're left with something very similar to what we've seen before. We're left with a final mass for stage one, and this includes everything that we've already seen: the mass of the payload plus the mass of the structure for stage two plus the mass of the propellant for stage two plus the mass of the structure for stage one. And just like before, after our burn, the mass of our propellant for that stage is totally used up. It's zero. Now, what we do after we've burned one stage is that we basically discard that stage's mass. We discard that structure. So we discard stage one's structure. Stage one structure. So when we discard the stage one structure, our initial mass decreases. Our initial mass was a very big number, which has decreased even more now. So our initial mass for our stage two can be said to be the mass of our payload plus the mass of our structure for stage two plus the mass of our propellant for stage two. Now notice that the mass of our structure for stage one is not included in this. So the mass of our structure for stage one and the mass of our propellant for stage one have been totally used up. So they've been totally used up, but we've experienced some initial change in velocity because of them. So that's good. Now we can burn our second stage, just like we've done countless times in our previous examples, our final stage for the stage 2 rocket, our final mass would just be the mass of our payload plus the mass of our structure for stage 2, taking into account that the mass of propellant for stage 2 has been completely consumed with our burn. So this would be our final mass, just the mass of our propellant, the mass of our payload, and the mass of our structure for stage 2. Now now since we have two stages, since we have two distinct stages, and I will bracket them right here. Since we have two distinct stages, we can write two distinct change in velocity equations. And what we can write that the change in velocity for stage 1 is equal to the exhaust velocity of stage 1 multiplied by the natural log of the initial mass for stage 1, divided by our final mass for stage 1. And likewise, the change in velocity for stage 2 is equal to the exhaust velocity we experience in stage 2 times the natural log of the initial mass of stage 2 divided by the final mass of stage 2. And to get the total mass, change in velocity that we experience, we can just say that the total change in total velocity is equal to the change in velocity experienced in stage 1 plus the change in velocity experienced in stage 2. So let's do an example with one of these problems. Let's try to find the change in total velocity of a SpaceX Falcon 9 rocket. Here's a picture of it. The SpaceX Falcon 9 rocket, which is not a single stage rocket, it's a double stage rocket. Here's the first stage of the rocket, stage 1, and here is the second stage of the rocket. And in comparison, the second stage is much smaller than the first stage. So let's get some numbers in and do some examples. And just doing a quick Google search, we find that the initial mass of the structure for stage 1, the initial mass of the rocket is 531,020 kilograms. The final mass of structure for stage 1 is equal to 135,320 kilograms. And the initial mass of structure for stage 2, the initial mass of stage 2, not the structure, is 109,720 kilograms. And the final mass of our rocket in stage 2 is equal to 17,050 kilograms. Now, we have to take into account one very big key, which is that the exhaust velocity is not the same. The exhaust velocity in stage 1 and stage 2 are different. The exhaust velocity in stage 1 is, the calculated exhaust velocity, I should say, is 3,050.91 meters per second. And the exhaust velocity in stage 2 is 3,384.45 meters per second. 0.45 meters per second. Now that we have these numbers, we can calculate our change in velocity for each stage, and we can calculate our total velocity, change in total velocity. Let's do that over here. So for the change in velocity, so let's do this in blue. So the change in velocity for stage 1 is equal to our exhaust velocity for stage 1, times the natural log of our initial mass for stage 1 divided by our final mass for stage 1, which is the same equation that we wrote right up here, the same equation we've written right up here. And we can calculate that right with a calculator. We can say that the initial mass for stage 1 is 531,020 kilograms divided by 135,320 kilograms, which gives us and we take this number to the natural log, and that gives us 1.367. Multiplying that by our exhaust velocity, we get 4,171 meters per second. So we get the change in velocity for stage 1 is equal to 4,171 meters per second. 171 meters per second. Now we can do the same thing for stage 2, and the change in velocity of stage 2. We can use the same equation, but we have to change all of these for 2's. We have to change these to 2's, and we can just work that out right here. The change in velocity of stage 2 would be 109,720 kilograms divided by 17,050 kilograms, which is equal to 6.435 natural log. We multiply that by our exhaust velocity, which is 3,384.45, and that gives us a change of velocity of 6,301 meters per second. So 6,301 meters per second. So the total change in velocity that the Falcon 9 experiences, the total change in velocity the Falcon 9 experiences is the change in velocity of stage 1 with the change in velocity of stage 2. So we can calculate that. That gives us a change in velocity of 10,472. So 10,472 meters per second. And we can say that this is the equivalent of about 10.5 kilometers per second. Not bad.